This is part 18 of the series Applications of Differentiation. In this part, we're going to investigate the idea of Newton's method for approximating the zeros of a function. Now, there are virtually an infinite number of functions which are either exceedingly difficult or impossible to find analytical solutions to. So we need another method to find working solutions to functions other than some analytical methods. And Newton's method is an excellent approach to that. And the idea here is this. If you have some function, let's call this function our target function, we can take a point x and draw the tangent line to that function at that point. If we follow that tangent line to the x-axis, we have a very grotesque approximation of where this function crosses the x-axis. As you can see, there's a great distance between b and where this function crosses the x-axis. However, if we take that b term and evaluate the function at that x value and draw another tangent line, we get a slightly better approximation for the zero of the function. If we continue this process up to point E, draw another tangent line, you can see that we progressively get closer and closer to the actual zero of the function. And this is the idea behind Newton's method for approximation of zeros of a function. It's based on a fundamental concept of differential calculus, and that is one of local linearity. So let's take a look at this idea of local linearity a little bit closer. So here we have some other function, and we can see that the function is significantly curved. If we draw a tangent line at some point, at, in this case, the minimum point, local minimum of this function, we can see that there's a great discrepancy between the actual curve and the tangent line. But as we approach, we can see that the function itself and the tangent line become closer and closer together. And as we get to 3 decimal point precision, the difference isn't all that far. And if we keep zooming in, we can see that eventually we get to a point where the two functions are indistinguishable, the tangent line and the actual function itself. So that's this idea of local linearity, that we can take a line, and if we get arbitrarily close to any particular point on that function, the tangent line is a close enough approximation to that function so that we can solve most any practical problems with it. So returning back to our original picture, this expression gives us the terms of the approximation of zeros of a function. If we consider that x sub n is an approximation, a first guess, if you will, at where the function will cross the x-axis, and we subtract from it the value of the function at that point divided by the derivative evaluated at that point, we will get the next approximation to the function. So this is x to the n, sub n plus 1. If we repeat this process, that is, take this approximation and then insert it into this expression, we will get yet another closer approximation to it. And you can repeat this process until you achieve the desired level of precision. Let's go ahead and look at Newton's method a little bit closer and see if we can determine where this thing comes from. So here, what we've done first is, this is the point slope form of a line. And if we take this y value and substitute in f of our initial guess, that gives us our y value. The slope is the slope of the tangent line at that point. So we have the slope of this line. And these two terms come down. Now solving for y, what we get in this form is the tangent line approximation to the function at this point. Now we're looking for the zero of this line. In other words, where does this line cross the x-axis? So we set y to 0, and our goal is to solve for x. So here we set it equal to 0, and we're going to distribute the f prime of x 1 into this expression. So we have x times f prime of x1 and minus f prime of x1 times x1. Now we need to solve for x, so this term has to be left on the right hand side, so we're going to move this term to the left hand side. Likewise, we need to get this term to the other side, so we subtract f of x1, and finally we divide by f prime of x1. And this gives us our specific form for Newton's method for the first approximation. And so this equation is a generalization of this specific approximation. Now before we go ahead and actually employ Newton's method, there are two caveats that we need to look at where Newton's method fails to find a zero. Now going back to our local linearity picture here, you can see that if we are moving through a point of tangency that passes an extreme value, the slope of the tangent line of the function is 0, which means this tangent line will never cross the x-axis because it's parallel to it. So if your approximations cross an extrema, then Newton's method will fail. The second caveat is if your approximations cross where the tangent line is undefined, that is, if you have a vertical tangent line of the function, then Newton's method will again fail. So it converges at all other points except for extrema and where the first derivative is undefined. And so I wanted to go through those before we actually apply it to see how this works. So let's go ahead and try an example to see how Newton's method works in practice. So we're to use Newton's method to approximate the zero of x squared minus 2, and we're told to use x equals 1 as an initial approximation. So if we write down Newton's method, we know that x2 equals x1 minus f of x1 over f prime of x1. So we're going to have the first derivative of this. So we know that f prime of x is 2x. Now evaluating this right side at our initial approximation, we get x2 equals 1 minus f of 1 over f prime of 1, which is 1 minus negative 1 over 2. And that gives us 1.5. Now if we do it again, x3 is 1.5 minus f of 1.5 over f prime of 1.5, and that gives us 1.466 continued. And we do this one more time. X sub 4 is 1.466 minus f of 1.466 over f prime of 1.466 gives us a final approximation 1.4124. Now before we move on to another problem, I'd like to show you a very nice method if you happen to possess one of these wonderful calculators, one of these wonderful TI-83 graphing calculators. There's a way to do Newton's approximation to take all the hassle out of it. And so that's what I'm going to show you at this point. So the first thing we're going to do is we're going to take our initial approximation, our initial guess, if you will, 1. And so we're going to take 1 and we're going to store that in x. So now we have our initial approximation stored. What I'm going to do then is I'm going to go to y equals, and I'm going to insert my function, which is x squared minus 2, and I'm going to insert my derivative function, 2x. Now I'm going to go back to the primary window, and we're going to enter this approximation method. And so we have our approximation is in x, so we say x minus, and to get the function f of x, we go vars, go over to y vars, function, and we select y1. We evaluate that at x, and then we divide that by the derivative function. So vars, y vars, function, and we're going to select y2 now, and evaluate that at x. Now the last piece, if we just enter this into the calculator, we actually get our first approximation, 1.5. But what I want to do is set it up so it's a little bit more automated, and I'm actually going to use this approximation and store it back into our x so that we can generate a second approximation. So I'm going to recall my function, second, enter, recalls the last function, store that result into our x. So I hit enter again, and now our new approximation has been stored in our x variable. Now that's all I need to do is recall the previous expression, hit enter, and I've got my second iteration. Do it again, and now I have my third. And you can continue this process until you see your decimals don't change to the desired precision. So that's just a quick little tip. If you happen to be lucky enough and have the money to purchase one of these TI-83s, I'm sure you can do the same thing on other calculators. The Casio makes a good graphing calculator. I just don't have one here. So let's go ahead and move on to another problem. In this problem we have 2x to the third plus x squared minus x plus 1. Let's go ahead and take our derivative. So that's going to be 6x squared plus 2x minus 1. So let's go ahead and set up Newton's method, and we have x1 minus f of x1 over f prime of x1. Now if you were to sketch this function, you would see that the 0 is going to be somewhere around -1. So that's what we're going to use as our first approximation. And I get -1.333 repeating. Let's do another one. -1.333 and f.333 over f prime -1.333, which gives us approximate -1.2433. And so one final approximation using 1.2433, we get 1.233 repeating, and it to 3 decimal places. Further iterations will give us the same approximation. So that's Newton's method, and now on to the next section.